Alright, so we had talked about how we will learn how to make covalent compounds, how to draw their structures. We are going to learn how to draw the structures of covalent compounds as well as the polyatomic ions. Remember when we talked about polyatomic ions in the previous week's videos, I said that they themselves, although contain charge on them, they are made up of non-metals and they are covalently made. They are made of covalent bonding to be exact. And what exactly is bonding? We learned about ionic and covalent bonding, but here in covalent bonding we'll actually see a bond being drawn out. So let's start by learning how to draw the structures and show the bonding in simple covalent compounds followed by polyatomic ions. So here is what you need to keep in mind, and these are the guidelines that you need to memorize, and every time you try to draw the structure of a covalent compound you should uh, keep them in mind and then make sure you don't deviate from following these guidelines. Number one, use chemical symbols for the various elements to write the skeletal structure of the compound. So that's something we all know. How do we show the structures? We'll use chemical symbols we find on the periodic table. That's how we will represent each kind of atom. The least electronegative atom will be placed in the central position. And that's very important. We have the electronegativity chart, and whenever you need to do this, I will provide you the chart or I will tell you who is in the center. So usually it's very easy. The atom that happens to occur only once in the formula is usually in the center. For example, if I have a formula CH4, which is a molecule of methane, well, there is one carbon and four hydrogens. Um, who is in the center? It is carbon because it only occurs once. Now, the example I gave you actually violates this rule. The least electronegative atom will be placed in the central position. When it comes to CH4, carbon is more electronegative than hydrogen, and yet it's in the center. So, when a situation like that arises, just try to draw the one that happens to occur only once in the center. If that's not the case, then pick the most electronegative. Now, why does the hydrogen occupy the side positions? Well, hydrogen always occupies terminal positions. So that rule supersedes this rule in the case of CH4. Halogens occupy terminal positions except when more electronegative elements are present. Okay, keep that in mind. And carbon often forms chains of carbon-carbon covalent bonds. We will not need to be aware of all of the rules in the kind of examples we will see in this course, but it's very good idea to actually keep these four rules in your head and always work with them whenever you try to draw structures. So first thing, okay, use chemical symbols for the various elements to write the skeletal structure of the compound, and then determine the number of valence electrons associated with each atom in the compound. Okay? So you need to be able to write the electron configuration. That's right, from chapter 2. Once you have the electron configuration, then you know which are the valence electrons, and you need to count how many total valence electrons are there in the entire molecule. For example, again with CH4, carbon has the electron configuration 1s2, 2s2, 2p2. The 2s2 and the 2p2 represent valence electrons. 2 plus 2 is 4. Hydrogen, on the other hand, only has one electron, which is its valence electron, but we have 4 hydrogens in CH4. That gives us a total of 4 valence electrons coming from the 4 hydrogens and 4 coming from the carbon, for a total of 8 valence electrons. This exercise is extremely important because if you mess this up, then the rest of the steps will be completely wrong. Now, what about polyatomic cations such as NH4 plus ammonium? How many valence electrons are there? Well, nitrogen has the electron configuration 1s2, 2s2, 2p3. 2s2 and 2p3, that's 2 plus 3, 5 valence electrons. Hydrogen would have each one 1 for a total of 4 because there are 4 hydrogen, NH4 plus. So that's 5 plus 4, 9. However, there is a positive charge on the whole ion. It's a cation. So what that means is that one of those 9 electrons has been removed from it. And so instead of having 9, there should be 8 valence electrons. On the other hand, if you have polyatomic anions with a negative charge, you would add the extra electrons to it that's equal to the total negative charge on it. For example, carbonate, which is CO3 2 minus. CO3 is the formula, 3 oxygens, 1 carbon, and 2 minus is the charge on it, or negative 2 is the charge on it. How many total electrons? Carbon, again with 1s2 2s2 2p configuration, has 4 valence electrons. Oxygen with 1s2 2s2 2p4 has 6 valence electrons, but there are 3 oxygens, so that's 6 times 3 18, plus the 4 coming from carbon, that's 22. But that's not where we are done. There is 2 minus charge on it as a superscript, so that's 22 plus 2 24 valence electrons. Please do this exercise correctly before you attempt the next steps. Now connect the central atom to each of the surrounding with single bonds. A single bond is just a straight line. We'll soon see the example of this. Next, complete octets of all the atoms bonded to the central atom. Give an octet to all of the side atoms. That's what it means, except hydrogen, which only needs 2 electrons. And when you are giving octets, you will give them as pairs, as lone pairs, 2 at a time on one side, and not 1 at a time. That's the difference between drawing the Lewis symbol and drawing the structure known as the Lewis structures. Once you, after the terminal atoms have an octet, the side atoms, there are the terminal atoms, they have an octet. Provide the central atom with an octet if valence electrons are still available. When you are giving these octets, you are using up the valence electrons that we have. And if still some remain, you can give an octet to the central atom. But what if none of them remain? If there are no valence electrons left to give to the central atom, an octet move lone pair electrons from terminal atoms to form a new bond with the central atom. And that's what will create a double bond or a triple bond. And then finally recheck that all atoms have the octet rule satisfied and that the total number of valence electrons are used. So it might not make all sense, but it will make sense currently as we look at an actual example. Let's try to make the structure of carbon dioxide. Notice I call it carbon dioxide. That's the name of this molecule. Now, who is going to be the central atom? Well, I said that the atom that happens to occur only once is usually the central atom. So is this the right form or is this the right form given here? If you said the second one, you are right. Also, if you go by electronegativity, oxygen has an electronegativity of 3.5, carbon has an electronegativity of 2.5. So who will be in the central? The least electronegative, which is carbon. And so this is how you draw it. Okay. Now, this is our result. Just put down OCO, leaving some space in between all of them, and then we will start with rule number 2. Find out the total valence electrons for each atom. So carbon has 4 valence, oxygen has 6, 6 times 2 is 12, for a total of 16. We have 16 electrons available to play with to get the right Lewis structure of the compound. Then use electron pairs to connect the carbon to each oxygen with a single bond. You are trying to connect the side atoms with the central atom. You are not trying to connect the side atoms with each other. Keep that in mind. Each and every time you do this, that's what you want to keep in mind. For simple structures we will look in our course, we will always connect the central atom with the side atoms, not the side atoms with each other. So this dash and this dash is called a bond, a covalent bond. And when we have only one dash, it's called a single bond. How many electrons are used up in this single bond? 2 electrons. Okay, so when we place this single bond, we used up 2 of the 16. When we place this single bond, we used up other 2 of the 16. So we used up 4. Keep in mind that you have 16 available. You used up 4. Then rule number 4, place electron pairs around the atoms, and you want to place them around the side atoms according to the rule number 4, where it was specifically spelled out in all details here. completing octets of all the atoms bonded to the central atom. So what we are trying to do is give octet to the side atoms here. So here, if we look at this part here, oxygen has how many electrons currently? Only two, 1, 2. Okay. We need to give it 8 because every time they bond covalently, everyone wants an octet. They are not bonding without wanting to gain an octet. That's the number one reason why they bond. So how many pairs of electrons do I give so that all together oxygen has 8? 3 pairs. So if we count each electron, that's 1, 2, 3, 4, 5, 6, and within the bond 2, 7, 8. Remember what we learned about covalent bond. Both of the electrons that are being shared can be said to be possessed by each of the atoms. So this oxygen can lay claim on the 2 electrons in this bond. This carbon can also lay claim on the 2 electrons in this bond. So that's 8 valence electrons for oxygen. Do the same for the other oxygen as well, but also make sure you are not going beyond the 16 electrons. So how many do we have when we do that here? This is 6, this is 6, that's 12, 13, 14, 15, 16. We are out. We only have 16 electrons and we use them all up. Does the central atom carbon have an octet? Let's count. That's 1, 2 here, 2 more here for a total of 4. We have 4 electrons. So what do we do? What's the next rule after that? Well, if we go to the last point of rule number 4, it says after the central terminal atoms have an octet, provide the central atom with an octet if valence electrons are available, but none are available. We don't have any available. Then what? If there are no if there are not enough valence electrons to give the central atom an octet, move lone pair electrons from terminal atoms to form a new bond with the central atom. Let's do that. What we'll do is we'll take one of these pairs from the side atom and we'll make a bond with this carbon here, and that will have 2 dashes, which is called a double bond. That's not going to change the total number of valence electrons for oxygen. It will still be 8, and we'll look at that, but carbon's total valence will go up by 2, as we will see. So when we do that for oxygen on the side, one side, and remove those 2 electrons a pair and make a bond here, and do the same thing from the other side, this is what we arrive at. Now count the total valence for all. Oxygen has 1, 2, 3, 4, and each bond is 2, 5, 6, 7, 8. This oxygen has 1, 2, 3, 4, each bond is 2, 5, 6, 7, 8. What about the central carbon? Does it have an octet? Yes. There are 4 bonds altogether, 2 double bonds. Each bond is equal to 2 electrons, so total of 4 here and 4 here for a total of 8 electrons. And did we use up all the 16? We not only need to not go above 16, but we also need to use all the 16 up. So 1, 2, 3, 4, 5, 6, 7, 8, and 8 coming from the central carbon. That's 8 plus 8, 16. And that's how we draw the Lewis structure of covalent compounds. And here was a very neat example of carbon dioxide. What about Lewis structures of polyatomic anions like carbonate? Earlier I said carbonate has 24 valence electrons, shown here counted for us. 4 coming from the carbon, single carbon, 18 from the oxygen, and 2 from this charge here. That's 24. Now you want to place the least electronegative element in the center, which is carbon, and also happens to occur only once, surrounded by 3 oxygens. Arrange your structure neatly, symmetrically. Okay, there is no exact way of doing it, but it has to be symmetrical so that we can see how every oxygen is equal. So now that we place them equidistant and we have 24 electrons available to us, let's start bonding them. We first give them single bonds, that's 1, 2, 3, 4, 5, 6. Then we give side atoms an octet, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We got all 24 here, and carbon does not have an octet, only has 6 electrons, 1, 2, 3, 4, 5, 6. So what shall we do? What do we do in a situation like this? Like it was said in the guidelines in rule number 5, take 2 electrons from one of the side atoms and make a bond with the central atom, and that's what we are doing here. You notice that these two electrons up here are missing here, and they are used to make a bond. Now carbon also has an octet, and everybody is satisfied, everybody is happy, and that's how we make the Lewis structures of polyatomic anions. Here are some examples for you to try. Try to make the Lewis structures of all five of these. Some of this you have seen previously, but don't go back and look at them. Carbon dioxide example we just looked at, and water also is in one of the previous chapter slides. Try to draw them without looking, and this exercise is very important, as drawing Lewis structure is very important.